Welcome to the Podlets podcast.
Good afternoon, everybody, and welcome to the Podlets podcast, a show in which we explore, some of the many things that make up kind of the cloud native landscape and things that are interesting to people who are playing with distributed systems. In this episode, we're going to talk about the network. My name is Duffy Cooley, and I'll be the lead of this episode. And with me, I have Nick.
Hey, what's up, everyone?
And Josh.
Hi.
And Mr. Scott Lowe is joining us as a guest speaker.
Hey, everyone.
Yay, welcome, Scott.
Thank you.
So in this discussion, we're going to try and stay away, like we do always, we're going to try and stay away from particular products or solutions that are related to the problem. And the goal of it is to really kind of dig into like what the network means when we refer to it as it relates to like cloud native applications or just application design in general. One of the things that I've noticed over time, and I'm curious like what y'all think, but like one of the things I've noticed over time is that people are kind of the mind that if they can't root cause a particular issue that they run into, they're like, that was the network, right? Have you all seen that kind of stuff out there?
Yes, absolutely. So in my previous life, before being a Kubernetes architect, I actually used my networking and engineering degree to be a network administrator for the Boeing company or the Boeing Corporation. And time and time again, someone would come to me and say, oh, this isn't working. The network's down. And I'm like, is the network down or is the server down? Because those are different things.
Yep.
Turns out it was usually the server.
I used to tell my kids that they would come to me and they would say the internet is down. And I would say, well, I don't think the entire internet is down. I think it's just our connection to the internet.
Exactly.
Dad, the entire global economy is just taking a total hit.
Exactly, right.
Yeah. I frequently tell people that my first distributed system that I ever had a real understanding of was the network, and it's interesting because it kind of like relies on some of the premises that like I think a good distributed system should, in that there is some autonomy to each of the systems, right? They are dependent on each other or even are intercommunicate with each other, but fundamentally, like when you look at routers and things like that, they are autonomous in their own way. Like there's work that they do exclusive to the work that others do, and exclusive to their dependencies, which I think is very interesting.
I think the fact that the network is a distributed system, and I'm glad you said that, Duffy. I think the fact the network is a distributed system is what most people overlook when they start sort of blaming the network, right? I mean, let's face it. In the diagrams, right, the network's always just this blob, right? Like, here's the network, right? It's this thing, this one singular thing, when in reality, what we have are like tens or hundreds of devices with the state of the network as a system distributed in little bitty pieces across all of these devices. And no way, aside from logging into each one of these devices, are we able to assemble what the overall state is. Right. Yeah. So even routing protocols, their entire purpose is to assemble some sort of common understanding of what the state of the network is, melding together not just, IP addresses, which are this abstract concept, but physical addresses and physical connections, and trying to reason and make decisions about that and how we send traffic across it. And it's far more complex than a lot of people understand. And I think that's why it's just like, oh, the network is down, right? When in reality, it's probably something else entirely.
Yeah, true.
Yeah, absolutely. Another good point to bring up is that each of these distributed pieces of this distributed system are in themselves like just basically like just a computer. A lot of times I've talked to people and they were like, well, the router is something special. I'm like, not really. Technically, like a Linux box could just be a router if you have enough ports that you plug into it, or it could be a switch if you needed to. You can just plug in the ports. Yeah.
Another good, interesting parallel there is like when we talk about like routing protocols, which are a way of a way that allow configuration changes to particular components within that distributed system to be known about by other components within that distributed system. I think there's an interesting parallel here between the way that works and the way that configuration patterns that we have for distributed systems work, right? Like if you wanted to make a configuration only change to a set of applications that make up some distributed system, you might go about like leveraging Ansible or one of the many other configuration models for this. And it's interesting. I think it's interesting because it kind of it represents sort of an evolution of that same idea, in that you're making it so that each of the components is responsible for informing the other components of the change, rather than taking the outside approach of my job is to actually push a change that should be known about by all of these components and down to them. It's an interesting parallel. What do y'all think of that?
I don't know. I'm not sure. Like, I'd have to process that for a bit. But I mean, are you saying like the interesting thought here is that in contrast to typical systems management where we push configuration out to something using a tool like an Ansible or whatever, these things are talking amongst themselves to determine state?
Yeah, it's like, I mean, there are patterns for this, like inside of distributed systems today, things like Kafka and Kafka and the Gossip protocol, stuff like this that actually allows all of the components of a particular distributed system to understand the common state or things that would be shared across them. And if you think about them, they're not all that different from a routing protocol, right? Like the goal being that you make these systems, you give the systems the ability to inform the other systems in some distributed system of the changes that they may have to react to. Another good example of this one, which I think is interesting, is like what they call when you have put a feature behind a flag, right? And you might have some distributed configuration model like a Redis cache or a database somewhere that you've held the running configuration of this distributed system. And when you want to turn on this particular feature flag, you want all of the components that are associated with that feature flag to enable that new capability. And some of the patterns for that are pretty darn close to the way that routing protocol models work.
Yeah, I see what you're saying, and actually that makes a lot of sense. I mean, if we think about things like gossip protocols or even consensus protocols like Raft, right?
Yeah.
They are similar to routing protocols in that they are responsible for distributing state and then coming to an agreement on what that state is across the entire system. And we even apply terms like convergence to both environments. Like we talk about how long it takes a routing protocol to converge. And we might also talk about how long it takes for an etcd cluster to converge after changing the number of members in the cluster or something of that nature. The point at which everybody in that distributed system, whether it be the network or etcd or some other system, comes to the same understanding of what that shared state is.
Yeah, I think that's a perfect breakdown, honestly, of pretty much every routing technology that's out there. Like, if you take a computer off the network, it takes a while, but eventually everyone will reconcile to the fact that, that node is gone now.
Yeah. I think one thing that's interesting, and I don't know how much of a parallel there is in this one, but like as we consider these systems, like with modern systems that we're building at scale, frequently we can make use of things like eventual consistency, in which it's not required per se for a transaction to be persisted across all of the components that it would affect immediately, just that they eventually converge, right? Whereas with the network, not so much, right? Like, like the network needs to be right now and every time, and there's not really a model for eventually consistent networks, right?
I don't know. Okay. I would contend that there is a model for eventually consistent networks, right? So certainly not on most organizations' relatively simple local area networks, right? But even if we were to take it and look at something like a Clos fabric, right, where we have top of rack switches, and if this is getting too deep for the non-networking folks, let me know, right? But where you take top of rack switches that are talking layer 2 to the servers below them or the endpoints below them, and they're talking layer 3 across a multi-link piece up to the top, right, to the spine switches. So you have leaf switches talking up spine switches, they're going to have multiple uplinks. If one of those uplinks goes down, it doesn't really matter if the rest of that fabric knows that that link is down, because we have this equal cost multipathing going across the fabric, right? And so in a situation like that, that fabric is eventually consistent in that it's okay if, me dropping link number 1 off leaf A up to, spine A is down, and the rest of the system doesn't know about that yet. But on the other hand, if you are looking at network designs where, convergence is being handled on active standby links or something of that nature, or there aren't enough paths to get from point A to point B until convergence happens, then yes, you're right. So I think it kind of comes down to network design and the underlying architecture, and there are so many factors that affect that, and so many designs over the years that it's hard to. I would agree, and from the perspective of, like, if you have an older network and it's been around for some period of time, right, you probably have one that is not going to be tolerant of a link being down, like it will cause problems.
That is another really great parallel in software development. I think another great example of that, right? Like if we consider for a minute like the circuit breaking pattern, or even like most load balancer patterns, right, in which you have some way of understanding a list of healthy endpoints behind the load balancer, and we're able to react when certain endpoints are no longer available. I don't consider that a pattern that I would relate to specifically to eventual consistency. Because I feel like that still has to be immediate, right? Like we have to be able to not send the new transaction to the dead thing. That has to stop immediately, right? And it does in most routing patterns that are described by multipath. There is a very, very time-sensitive mechanism that allows for the redispersal of that traffic across known paths that are still good, right? And the amazing amount of work that protocol architects and network engineers go through to understand just exactly how the behaviors of those systems will work, such that we don't see traffic black holed in the network for a period of time, right? So that we don't send traffic to the trash when we know, or we have for a period of time while things converge. It's really it has a lot going for it.
Yeah, I would agree. I think the interesting thing about discussing eventual consistency with regards to networking is that, even if we take a relatively simple model like the DoD model, where we only have 4 layers to contend with, right? And we don't have to go all the way to the 7-layer OSI model, but even if we take a simple layer like the DoD 4-layer model, we could be talking about, the rapid response of a device connected at layer 2, but the less than rapid response of something operating at layer 3 or layer 4, right?
Yeah.
And so in the case of a network where we have these discrete layers that are intentionally loosely coupled, which is another topic we could talk about from a distributed system perspective, right? Yeah. We have these layers that are intentionally loosely coupled. We might even see consistency and the application of the CAP theorem behave differently at different layers of that model.
That's right. Yeah, I think this is I think it's fascinating, like how much parallel there is here. Like as you get into like deep architectures around software, you're thinking of these things as it relates to like these distributed systems, especially as you're moving toward more cloud native systems in which you start employing things like control theory and thinking about the way that and thinking about the behaviors of those systems both in aggregate, like some component of my application, can I scale this particular component horizontally or can I not? Like how am I handling state? And so many of those things have parallels to the network that I feel like it kind of highlights, I'm sure, what everybody has heard a million times, that there's nothing new under the sun, right? Like there's a million things that we can learn from things that we've done in the past.
Yeah, I totally agree. Where like I recently been getting more and more development practice, and something that I do sometimes is I'll like draw out like how all of my functions and all my methods and things like that interact with each other across a consistent code base. And lo and behold, when I draw everything out, dang, it sure does look a lot like a network diagram. all these things have to flow together in a very specific way, and you expect the kind of returns that you're looking for. It looks exactly the same. It's kind of the, how an atom kind of looks like a galaxy from our diagram. Like all these things are extrapolated across like
Yeah, totally.
different models. Or an atom looks like a solar system, which looks like a galaxy.
So Nicholas, you said were you a network administrator at Boeing?
I was a network engineer at Boeing.
So, as you were sitting there talking, Duffy, so I thought back to you, Nick. I think a lot of times, I have a personal passion for helping people continue to grow and evolve in their career and not being stuck. And I talked to a lot of networking folks, probably dating because of my involvement along with you, Duffy, back in the NSX team, right? But folks being like, oh, I'm just a network engineer. I don't, there's so much for me to learn if I have to go learn Kubernetes. Like I wouldn't even know where to start. But like this discussion to me underscores the fact that if you understand how a network is a distributed system and how these theories apply to a network, then you can extrapolate those concepts and apply them to something like Kubernetes or other distributed systems, right? And immediately begin to understand, oh, okay, well, this is how these pieces talk to each other. This is how they come to consensus. This is where the state is stored. This is how they understand and exchange state. Oh, okay, yeah, I got this. And it's really
if you
not
want to go down that path, like the control plane of your cluster is just like your central routing backbone, and then the kubelets themselves are just your edge switches going to each of your individual like smaller network, and then the pods themselves are the nodes inside of the network, right? You can easily boop, 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 boop. Like, look at that. Holy crap. It looks exactly the same.
Sure does.
Yeah, that's a good point.
I mean, I think another interesting part is like when you think about like how we characterize systems, like where we learn that, like where that skill set comes from. I think you raise a very good point. Like I think it's important to. I think it's an easier, maybe slightly easier thing to learn inside of networking how to characterize that particular distributed system because of the way the components themselves are laid out and in such a common way, right? Whereas like when we start looking at different applications, we find a myriad of different patterns with particular components that may behave slightly differently depending, right? Like there are different patterns within software, like almost on a per application basis. Whereas like with networks, they're pretty consistently applied, right? And every once in a while there'll be kind of like a new pattern that emerges that just changes the behavior a little bit, right? Or changes the behavior like a lot, but but at the same time consistently across all of those things that we call data center networks or what have you. And so to learn to troubleshoot, though, I think the key part of this is to be able to spend the time and the effort to actually understand that system. And yeah, it's like whether you light that fire with networking or whether you light that fire with like just understanding how to operationalize applications or even just developing and architecting them, all of those things come into play, I think.
Totally agree. So I'm actually kind of curious. The three of us have been talking quite a bit about networking from the perspective that we have, which is more infrastructure focused. But Josh, you have more of a developer focused background. What's your interaction and understanding of the network and how it plays?
Yeah, I've always been a consumer of the network. It's something that is set behind an API and some library, right? I call out to something that makes a TCP connection or an HTTP interaction, and then things just happen. And I think what's really interesting hearing you all talk, and especially the point about network engineers getting into the distributed system space, is that I really think that as we started to put infrastructure behind APIs and made it more and more accessible to people like myself, app developers and programmers, we started, and by we, I'm obviously generalizing here, but we started owning more and more of the infrastructure. So when I go into teams that are doing big Kubernetes deployments, it's pretty rare that it's the conventional the infrastructure and networking teams that are standing up distributed systems. Kubernetes or not, right? It's a lot of times a bunch of app developers who have maybe what we call DevOps, whatever that means, but they have an application development background. And they understand how to interact with APIs, how to write code that respects or interacts with their infrastructure, and they're standing up these systems. And I think one of the gaps that really creates is a lot of people, including myself, just hearing you all talk, like we don't understand networking at that level. And when stuff falls over and it's either truly the network or it's getting blamed on the network, it's oftentimes just because we truly, truly don't understand a lot of these things, right? Encapsulation, meshes, whatever it might be. We just don't understand these concepts at a deep level. And I think if we had a lot more people with network engineering backgrounds shifting into the distributed system space, it would alleviate a bit of that, right? Bringing more understanding into the space that we work in nowadays.
I wonder if it maybe also would be a benefit to have like more cross discussions, kind of like this one, between developers and infrastructure kind of focused people, because we're starting to see, like, as we're crossing boundaries, we see that the same things that we're doing on the infrastructure side, you're also doing in the developer side, like CAP theorem, as Scott mentioned, which is the idea that you can have 2 out of 3 of consistency, availability, and partitioning. That also applies to networking in a lot of ways. Like, you can only have a network that is either like consistent or available, but it can't handle partitioning, or it can be consistent and handle partitioning, but it's not always going to be available, that sort of thing. These things that apply from a software perspective also apply to us, but we think about them as being so completely different.
Yeah, I totally agree. I mean, I really think like on the app side, a couple of years ago, I really just didn't care anything outside of the JVM. Like, my stuff ran in the JVM, and if it got out to the network layer of the host, like, just didn't care, no need to know about that at all. But ever since cloud computing and distributed systems and everything became more prevalent, the overlap has become extremely obvious, right? In all these different concepts. And it's been really interesting to try to ramp up on that.
Yeah, and I think Scott and I both do this. I think this. I imagine actually this is true of all 4 of us, to be honest. But I think that it's really interesting when you are out there talking to people who do feel like they're stuck in some particular role, like that they're specialists in some particular area, and we end up having the same discussion with them over and over again. Like look, that may pay the bills right now, but it's not going to pay the bills in the future, and so. The question becomes like, how can you, as a network engineer, rely on take your skills forward and not feel as though you're just going to have to like learn everything all over again, right? And I think that one of the things that network engineers are pretty decent at, right, is characterizing networks, characterizing those systems, and being able to troubleshoot them, and being able to do it right now, and being able to like firefight. Those capabilities and those skills are incredibly valuable in software development and in operationalizing applications and in SRE models. I mean, they're like all of those skills transfer. So if you're out there and you're listening and you feel like I will always be a network engineer, consider that you could actually take those skills forward into some other role if you chose to.
Yeah, totally agree. I mean, look at me. Look at the lofty career that I've come to.
Mm-hmm.
I would also say that, like, the fascinating thing to me, and one of the reasons I launched, and I don't say this to like try and plug it, but just as a way of talking about the reason I launched my own podcast, which is now part of Packet Pushers, was exploring this very space. And that is, like, we've got folks like Josh, who comes from the application development space and is now being, in a way, forced to own and understand more infrastructure. And we've got the infrastructure folks who now, in a way, whether it be through the rise of cloud computing and abstractions away from physical items, are being forced kind of up the stack, right? And so they're coming together. And so this idea of like, what does the future of the the folks that are kind of like in our space, what does that look like? Like, how much longer does a network engineer really need to be deeply versed in all the different layers, because everything's been abstracted away by some other type of thing, whether it's VPCs or Azure VNets or whatever the case is, right? I mean, you've got companies bringing the VPC model to on-premises networks, right? And so it's like, as APIs become more prevalent, as everything gets sort of abstracted away, what does the future look like? What are the most important skills? And it seems to me that it's these concepts that we're talking about, right? This idea of distributed systems and how distributed systems behave and how the components react to one another, and understanding things like the CAP theorem that are going to be most applicable, rather than the details of troubleshooting BGP or understanding, AWS VPCs or whatever the case may be.
Mm-hmm.
I think there's always going to be a place for the people who know how things are running under the hood from a physical layer perspective, that sort of thing. There's always going to be the need for the graybeards, right? Even in software development, we still have the people who are slinging kernel code in C, and they're the best. We salute you, but that is not something that I'm interested in doing for sure. We always need someone there to pick up the pieces, as it were. But I think that that having just being like, I'm a Cisco guy, I'm a Juniper guy. I know how to telnet or RSH into the switch and execute these commands, and suddenly I've got this port is now trunked to this VNet crap. I was like, Nick, remember your training. Mm-hmm. How to issue those commands. I think that them isn't necessarily going away, but it will be less in demand in the future.
I'm curious to hear Josh's perspective as having to own more and more of the infrastructure underneath. Like, what seems to be the right path forward for those folks?
Yeah, I mean, unfortunately, I feel like a lot of times it just ends up being trial by fire, and it probably shouldn't be that. But the amount of times that I've seen a deployment of some technology fall over because we overlapped a CIDR range or something like that is crazy, because we just didn't think about it or really understand it that well. Using one, protocol you just described, BGP, I never, ever dreamt of what BGP was until I started using distributed systems, right? And started using BGP as a way to communicate routes. And the amount of times that I've messed up that connection because I don't have a background in how to set that up appropriately, it's been rough. I guess my perspective is that the technology has gotten better overall. And I'm mostly, obviously, in the Kubernetes space, is speaking to the technologies around a lot of the container networking solutions, but I'm sure this is true overall. It seems like a lot of the sharp edges have been buffed out quite a bit, and I have less of an opportunity to do things terribly wrong. And I've also noticed, for what it's worth, a lot of folks that have my kind of background are going out to the AWSs, the Azures of the world, and they're using all these abstracted networking technologies that allow them to do really cool stuff without really having to understand how it works. And they're oftentimes going back to their networking team on-prem when they have on-prem requirements and being like, it should be this easy, or X, Y, and Z. And they're almost pushing the networking team to modernize a bit and make things simpler based on experiences they're having with these cloud providers.
Yeah. What do you mean I can't create a load balancer that crosses between these two disparate data centers as easily as just issuing a single command? Doesn't this just exist from a networking standpoint?
Even just the idea that you can issue an API command and get a load balancer, just that idea alone, right? The thousands of times I have heard that request in my career, right?
And the actual work under the hood to get that to work properly it's a lot. There's a lot of stuff going on.
Absolutely, yeah. Especially when you're in the plumbing, if you're going to create a load balancer with an API, well, then what API does the load balancer use to understand where to send that traffic when it's being balanced, right? How do you handle discovery? How do you handle, obviously, yeah, there's no shortage of the amount of work there.
Yeah.
Yeah, that's a really good point. I mean, I think, sometimes it's easy for me to think about some of these API-driven networking models and the costs that come with them, the hidden costs that come with them. An example of this is if you're in AWS and you have connectivity between two availability zones, or it actually could be any cloud, it doesn't have to be AWS, right? If you have connectivity between two different availability zones and you're relying on that to be reliable and consistent and definitely not to experience a partition, then how do what tools do you have at your disposal? What guarantees do you have that network is even operating in a way that is responsive, right? What and in a way, this is kind of taking us toward like sort of the observability conversation that I think we've talked a little bit about in the past. Because I think it highlights the same set of problems again, right? Like you have to understand, you have to be able to provide the consumers of any service, whether that service is plumbing, whether it's networking, whether it's your application that you've developed that represents a set of microservices. You have to provide everybody a way to, or you have to provide the people who are going to answer the phone at 2 a.m, or even the robots that are going to answer the phone at 2 a.m. You have to provide them some mechanism by which to observe those systems as they are in use. And I don't know. I'm not convinced that very many of the cloud providers do that terribly well today. Like I feel like I've been burned in the past without actually having an understanding of the state that we're in. And so it's interesting. Maybe the software development team can actually start pushing that down toward the networking vendors of the world.
Yeah, that would be great. I mean, I've been recently using a managed Kubernetes service. I've been kicking the tires on it a little bit. And yeah, there's been a couple times where I've just been got by networking issues. I'm not going to get into what a CNI, a container network interface, or any of the technologies around that. We're going to talk about that another time. But the CNI that I'm using in this managed service, it was just so wonky and weird, and it was failing from a network standpoint. The actual network was failing because, in a sense, because the IP addresses for the nodes themselves or the pods wasn't being released properly, and because of RBAC. And so the rules associated with my account could not remove IP addresses from a node in a network because it wasn't allowed to. And so from a networking perspective, I ran out of IP addresses in my very small CIDR.
And this could happen in a database, right? Like this could happen in a cache of information. This could happen, like in pretty much the same pattern that you're describing is absolutely relevant in both of these fields, right? Like, and that's the fascinating thing about this is that I think when we talk about the network generally in these nebulous terms, and that it is like a black box, and I don't want to know anything about it. I don't want to learn about it. I don't want to understand it. I just want to be able to consume it via an API, and I want to have the expectation that everything will work the way it's supposed to. I think it's fascinating that, like, on the other side of that API are people maybe just like you who are doing their level best to provide to chase the CAP theorem to its happy end, and like figure out how to actually give you what you need out of that service, so like, empathy I think is important.
Absolutely. To kind of bring that to a kind of interesting thought that I just had, where on both sides of this like chasm or whatever it is between networking and development, the same principles exist, like we've been saying, but just to kind of elucidate on it a little bit more, it's like on one side you have like, I need to make sure that these etcd nodes communicate with each other and that the data is consistent across the other ones. So we use a protocol called Raft, right? And so that's a eventually consistent tool. Then that information gets sent onto a network, which is probably using OSPF, which is open shortest path first routing protocol, to become eventually consistent on the data getting from one point to the other by opening the shortest path possible. And so these two things are very similar. They're both these communication protocols, which is, I mean, that's what protocol means, right? A standard for communication. But they're just so like different layers, obviously, of the OSI model. But people don't put them together, but they really are. And we keep coming back to that, where it's all kind of the same thing, but we think about it so differently. And I'm actually really appreciating this conversation because now, like, I'm having like a galaxy brain moment. We're like,
Totally. Another really interesting one, right? Like another galaxy brain moment I think that is interesting. It's like if you think about so let's break them down like TCP and UDP. These are interesting patterns that actually do totally relate, again, just in software patterns, right? Like in TCP, the guarantee is that every datagram, if you didn't get the entire datagram, you'll understand that you're missing data and you will request a new version of that same packet. And so you can provide consistency in the form of retries or repeats if things don't work, right? Not dissimilar from the ability to understand, like, that whether you're checksumming data across the network or like in a particular database, if you make a query for a bunch of information, you have to have some way of understanding that you got the most recent version of it, right? Like etcd supports this in some ways, or etcd supports this by using the revision, right? Like understanding what revision you received last and whether that's the most recent one. And other software patterns kind of follow the same model. And I think that's also kind of interesting. Like, like we're still using the same primitive tools to solve the same problems, whether we're doing it at a software application layer or whether we're doing it down in the plumbing at the network application, at the network layer. These tools are still very similar. Another example is like UDP, where it's like basically there are no repeats. You either got the packet or you didn't, which sounds a lot like a kind of an event stream to me in some ways, right? Like it's very interesting. Like you figure, like, I put it on the line, you didn't get it, it's okay, I'll put another one on the line here in a minute, and you can react to that one, right? Like it's kind of an interesting overlap.
Yeah, totally.
Yeah, the comparison to event streams or message queues, right, is an interesting one that I hadn't considered before. But yeah, there are certainly parallels between, saying, okay, I'm gonna put this on the message queue and wait for the acknowledgement that somebody has, taken it and taken ownership of it, as opposed to an event stream where it's like, this happened, I emit this event. If you get it and you do something with it, great. If you don't get it and you don't do something with it, great, because another event's going to come along soon. So there you go.
Yep.
I'm going to go down a kind of a weird topic, kind of associated with what we were just talking about, but I'm going to get a little bit more into the weeds of networking. And this is actually going to be kind of directed at Josh in a way. So talking about like the kind of parallels between networking and development. In networking, at least with TCP networking, there's something called CSMA-CD, which is carrier sense multi. I can't remember what the A stands for. And then the CD is multi-access, and then CD is collision detection. And so basically what that means is that whenever you send out a packet on the network device itself is listening on the network for any collisions. And if it detects a collision, it will refuse to send a packet until a certain period of time, and they'll do a retry to make sure that these packets are getting sent as efficiently as possible. There's an alternative to that called CSMA-CA, which was used by Mac before they switched over to using a Linux-based operating system and then putting a fancy UI in front of it, which collision avoidance would listen and try and, I can't remember exactly, it would time it differently so that it would totally just avoid any chance that there could be a collision. It would like make sure that no packets are being sent right then and then send a packet out. And so I was wondering if something like that exists in the realm of like the communication path between applications.
Is a collision two of the same packets being sent, or what exactly is a collision?
Two of any packet, so basically any data going back and forth.
What makes it a collision?
It's the idea that you can only transmit one message at a time, because if they both populate the same media, it's trash. Both of them are trash.
And how do you qualify that? Do you receive an ACK from the system, or?
No, there's just nothing returned, essentially. So it's like literally like the electrical signals going down the wire physically collide into each other, and then the signal breaks.
Oh, I see.
Mm-hmm.
Yeah, I'm not sure. I mean, I think there's some parallels to that, maybe with like queuing technologies and things like that, but can't think of anything on like direct app dev side.
Okay. Anyway, sorry for that tangent. I just kind of wanted to go down that little rabbit hole a little bit. It was like, while we were talking about networking, I was like, oh yeah, like I wanted to see how deep down we can make this parallel go. And so that was the direction I went.
Of course, that CSMA CD, a piece is like seriously old school, right? Yeah. Because it only applied to half duplex Ethernet, and as soon as we went to full duplex Ethernet, then it didn't matter anymore.
That's true. I totally forgot about that as well. Yeah, I totally forgot about that. Yeah, with full duplex, we totally just space on that. This is, damn, Scott, way to make me feel old.
Well, satellite stuff too, right? It's not just, it's actually any shared media upon which you have to, where if the signals overlap, you're not going to be able to make it work, right? And so, it is interesting. It's actually, it is an interesting parallel. I'm struggling to think of to think of an example of this as well. I mean, like my brain is kind of going towards circuit breaking, but I don't think that that's quite the same thing. It's sort of the same thing in that in a circuit breaking pattern, the application that is making a request has the ability, obviously because it is the thing making the request, to understand that the target it's trying to connect to is not working correctly. And so it is able to make an almost instantaneous decision, or at least a very timely decision about what to do when it detects that state. And so that's a little similar in that you can, in that from the requester side, you can do things if you see things going awry. And really, in reality, in the circuit breaking pattern, we're making the assumption that like only the application making the request will ever get that information fast enough to react to it.
Yeah, where my head was kind of going with it, but I think it's pretty off. Is like unlike in like a low level piece of code, like maybe something you write in C where you implement your own queue in memory, and then like multiple threads are firing off at the same time, and there's no like lock system or mechanism if two threads contend to put something in the same memory space that queue represents. Again, like that's really going down the rabbit hole. I can't even speak to like to what degree that's possible in modern programming, but that was where my head was.
Yeah, that's a good point.
Yeah, I think that's actually a pretty good analogy because the key commonality here is some sort of shared access, right? Multiple threads accessing the same stack or memory buffer. The other thing that came to mind to me was like some sort of session multiplexing, right? Where you're running multiple application layer sessions inside a single sort of network connection, and those network sessions getting commingled in some fashion, whether through identifiers or sequence numbers or something else of that nature, and therefore, garbling the ultimate communication that's trying to be, sent.
Yeah. Locks are exactly the right direction, I think. That's a very good point.
Yeah, I think that makes perfect sense. Good. All right. Yes, we nailed it.
Good job.
Can you think of a software pattern? Can anybody here think of a software pattern that maybe doesn't come across that way? Like when you're thinking about some of the patterns that you see today in cloud native applications, is there like a counterexample, something that the network does not do at all, or
That's interesting. I'm trying to think where I'm like event streams. No, that's just straight up packets.
I feel like we should open up one of those old school Java books of like 9,000 design patterns you need to know, and we should go one by one and be like, what about this?
Yeah.
There's probably something. I can't think of it off the top of my head.
Yeah, me neither. I was trying to think of it. I mean, like I can think of a myriad of things that do crossover, even like the idea of like only locally relevant state, right? Like that's like a cam table on a switch. That's only locally relevant. Because once you get outside of that switching domain, it doesn't matter anymore. And it's it's like there's a ton of those things that like totally do relate, but I'm really struggling to come up with one that doesn't. One thing that's actually interesting is I was going to bring up, we mentioned the cap theorem, and it is an interesting one that you can only pick like 2 of 3 of consistency, availability, and partition tolerance. And I think, when I think about the way that networks solve or try to address this problem, they do it in some pretty interesting ways. Like, I mean, if you were to consider like what do you call it? Spanning tree, right? The idea that there can really only be one path through a series of broadcast domains, because if you have multiple paths, then obviously you're going to get duplicity, and things are going to get bad because you're going to have packets that are addressed the same things across, and you're going to have all kinds of bad behaviors, switching loops and broadcast storms and all kinds of stuff like that. So so Spanning Tree came along, and Spanning Tree was invented by an amazing woman engineer who created it to basically ensure that there was only one path through a set of broadcast domains. And in a way, this kind of solves that cap theorem, because you're getting to the point where you've said, like, since I understand that for availability purpose, I only need one path through the whole thing. And so to ensure consistency, I'm going to turn off the other paths. And to allow for partition tolerance, I'm going to enable the system to learn when one of those paths is no longer viable so that it can re-enable one of the other paths. Now, the challenge, of course, is that there's a transition period in which we lose traffic because we haven't been able to open one of those other paths fast enough, right? And so it is interesting to think about how the network is trying to solve the same set of problems that's described by the CAP theorem that we see people trying to solve with software routine.
Oh, no, I mean, I totally agree. And in a case like Spanning Tree, you are sacrificing availability, essentially, right, for consistency and partition tolerance. Mm-hmm. In that, when the network achieves consistency, then availability will be restored. And there's other ways of doing that. So as we move into systems like, I mentioned class fabrics earlier, right? A class fabric is a different way of establishing establishing a solution to that, and that is saying, at layer 2, I'll have sort of multiple connections, but I will weight those connections using a higher level protocol, and I will sacrifice consistency in terms of how the routes are exchanged to get across that fabric in exchange for availability and partition tolerance. Mm-hmm. So it's just a different way of solving the same problem, and using a different set of tools to do that, right?
I also find it I personally find it kind of funny that, in the CAP theorem, at no point do we mention complexity, right? Like we're just trying to get all three, and we don't care if it's complex. We just and at the same time, as a consumer of all of these systems, you care a lot about the complexity. I hear it all the time. Whether that complexity is in the way that the API itself works, or even in this episode we were talking about, I maybe don't want to learn how to make the network work. I'm busy trying to figure out how to make my application work. Right? Like cognitive load is a thing, right? Like I can only really focus on so many things at a time. Where am I going to spend my time? Am I going to spend it learning how to do plumbing, or am I going to spend it actually trying to write an application that solves my business problem? Right? It's an interesting thing.
So something that we kind of touched on a little bit ago, and I wanted to come back to as we're kind of wrapping up. So we mentioned software-defined networking, which is pretty well defined. It's how do you define how your network wants to look via whatever software it is that you're using. How do we think that software-defined networking played into the rise of cloud technologies altogether?
Say that again. Sorry.
It's all good. So with the rise of software-defined networking, how did that play into the adoption of cloud-native technologies?
I think that's actually one of the more interesting overlaps in the space, because I think, to Josh's point again, this is where we were taking. I worked for a company called Nicira, in which we were virtualizing the network, and this was fascinating because effectively we're looking at this as the network as a software service that we had to bring up and build and build reliably and scalable, reliably and consistently, and we had to solve all those same problems, but we needed to do it with an API, because we couldn't make the assumption that the way that networks were being defined today by going to each component and configuring them or using protocols was actually going to work in this new model of software-defined networking. And so we had an incredible amount of engineers who were really focused from a computer science perspective on how to effectively reinvent that network as a software solution. And I think I do think that there's a huge amount of crossover here. This is actually where I think the waters meet. Between the way that developers think about the problem and the way that network engineers think about the problem. But it's been a rough road, I will say. I'll say that SDN, I think, has definitely thrown a lot of network engineers off onto their heels. Because they're like, wait, but that's not a network, and because I can't look at it and characterize it in the way that I am accustomed to looking at and characterizing the other networks that I play with. And then from the software side, you're like, but maybe that's okay, right? Like maybe that's enough. It's really interesting.
I don't know enough about the details of how AWS or Azure or Google are actually doing their networking. Like, and I don't even know, and maybe you guys all do know, but like, I don't even know that aside from a few tidbits here and there, that AWS has even kind of divulged the details of how things work under the covers for VPCs, right? But I can't imagine that any modern cloud networking solution, whether it be VPCs or VNets or whatever, doesn't have a significant software-defined aspect to it. We don't need to get into the definitions of what SDN is or isn't. That was a big discussion Duffy and I had 6 years ago, right?
Yeah.
But there has to be some part of it that is taking and using the concepts that are common in SDN, right? And applying that just as in the same way as the cloud vendors are using the concepts from compute virtualization to enable what they're doing. I mean, like, the reality is that the work that was done by the Cambridge folks on Zen was a massive enabler for AWS, right? The work done on KVM, also a massive enabler for lots of people. I think GCP is KVM based. And vSphere and what VMware did as well. I mean, all of this stuff was massive enablers for what we do with compute virtualization in the cloud. I have to think that, whether it's, even if it wasn't necessarily directly stemming out of Martin Casado's OpenFlow work at Stanford, right? That a lot of these software-defined networking concepts are still seeing use in the modern clouds these days. And that's what enables us to do things like, issue an API call and have an isolated network space with its own address space and its own routing instantiated in some way and managed.
Yeah, and on that latter point, as a consumer of this new software-defined nature of networking, like, it's amazing the amount of, I'm sorry to use like a blanket marketing term here, but agility that it's added, right? Because it's turned all these constructs that I used to file a ticket and follow up with people into self-service things that when I need to poke holes in the network, hopefully, the rights are locked down so I can't just open it all up. But assuming I know what I'm doing and the rights are correct, it's totally self-service for me. I go into AWS, I change a security group rule, and boom, the ports have changed. And it never looked like that prior to, this full takeover of what I believe is, SDN almost end to end in the case of AWS and so on. So it's really just, not only has it made people like myself have to understand more about networking, but it's allowed us to self-service a lot of the things that I would imagine most network engineers were probably tired of doing anyways, right? Like, how many times do you want to go to that firewall and open up that port? Are you really that excited about that? I would imagine not. So,
well, I can speak from experience, and I think a lot of network engineers kind of get into that field because they really love control. And so they want to know what these ports are that are opening. And it is kind of scary to be like, this person just opened up these ports. Wait, what? Like, without them even totally knowing.
Mm-hmm.
Now, that was I was generalizing. I was more speaking to myself. I was being self-deprecating. It does not apply to you, listener.
I mean, it is a really interesting point, though. I mean, do you think it makes the networking people or network engineers maybe a little bit more into the realm of observability and like knowing when to trigger when something has gone wrong? Does it make them more reactive in their role, I guess? Or maybe self-service is not as common as I think it is. It just, from my point of view, it seems like with SDNs, the ability to modify the network, more power has been put in the developer's hands is kind of how I look at it,
I definitely agree with that. It's interesting. It's like if we go back a few years, there was a time when like all of us in the room here, I think, are employed by VMware, and so it's there was a time when VMware's thing was, like the real value of, or one of the key values that VMware brought to the table was the idea that a developer could come and say, and give me 10 servers, and that you could just call an API or make a you could quickly provision those 10 servers on behalf of that developer and hand them right back, right? You wouldn't have to go out and get 10 new machines and put them into a rack, power them and provision them and go through that whole process, that you could actually just stamp those things out, right? And that is absolutely a parallel to the network piece as well. And that, I mean, if there's nothing else that SDN did bring to the fore, it is that, right? That you can get that same capability of just stamping out virtual machines, but with networks, right? That the API is important in almost everything we do, whether it's a service that you are developing, whether it is the network itself, whether it's the firewall. That, like, we need to do these things programmatically.
I agree with you, Duffy, although I would contend that the one area that, and I'll call it on-premises SDN, shall we say, right? Which is, the people putting in SDN solutions. I'd say the one area, at least in my observation, that they haven't done well is that self-service model. Like in the cloud, self-service is paramount, right? To Josh's point, like they can go out there, they can create their own VPCs, create their own subnets, create their own, NAT gateways, internet gateways, their own security groups, load balancers, blah, blah, all that, right? But it still seems to me that even though we are probably, 90, 95% of the way there, maybe farther in terms of on-premises SDN solutions, right? That you still typically don't see self-service being pushed out in the same way you would the public cloud, right? Like that's almost the final piece that is needed to bring that cloud experience to the on-premises environment.
That is an interesting point. I think from an infrastructure as a service perspective, it falls into that realm. It's a problem to solve in that space, right? So when we look at things like OpenStack and things like AWS and things like GKE, or not GKE, but GCE and areas like that, it is a requirement that if you're going to provide infrastructure as a service, that you provide some capability around networking. But at the same time, if we look at some of the platforms that are used for things like cloud native applications, things like Kubernetes, what's fascinating about that is that like we have we have agreed on a least common. We've agreed on an abstraction of networking that is maybe, I don't know, maybe a little more pre-cooked. You know what I mean? Like, in the assumption within like most of the platforms as a service that I've seen, the assumption is that when I deploy a container, or I deploy a pod, or I deploy some function as a service, or any of these things, that the networking is going to be handled for me. Like, I shouldn't have to think about whether it's being routed to the internet or not, or routed back and forth between these domains. I should, if anything, only have to actually give you intent, be able to describe to you the intent of what could be connected to this, and what ports I'm actually going to be exposing, and that the platform actually hides all of the complexity of that network away from me, which is an interesting balance to strike.
So this is like one of my favorite favorite things, like one of my favorite distinctions to make, right? And that is like, this is the two worlds that we've been talking about, applications
Absolutely.
and infrastructure, right? And the perfect example of these different perspectives. And you even said it in your talk there, Duffy, like from an IaaS perspective, it is considered a given that you have to be able to say, I want a network, right? But when you come at this from the application perspective, you don't care about a network. You
Nope.
just want network connectivity, right?
Mhm.
And so when you look at the abstractions that IaaS vendors and solutions and products have created, then they are IaaS centric. But when you look at the abstractions that have been created in the cloud native space, like within Kubernetes, they are application centric, right? And so we're talking about infrastructure artifacts versus application artifacts, right? And they end up meeting, but they are coming at this from two different, very different perspectives.
Yeah. Yeah, I agree. All right. Well, that was a great discussion. I imagine that we're probably going to get into. I at least have a couple of different networking discussions that I wanted to dig into. And this conversation, I hope that we've helped kind of draw some parallels back and forth between the way that I mean, both there's some empathy to spend here, right? I mean, like the people who are providing the service of networking to you in your cloud environments and in your data centers, are solving almost exactly the same sorts of availability problems and capabilities that you are trying to solve with your own software. And I think that itself is a really interesting takeaway. Another one is that, like, again, there's nothing new under the sun. Like, the problems that we're trying to solve in networking are not different than the problems that you're trying to solve in applications. We have far fewer tools, and we generally networking. Network engineers are kind of focused on like specific changes that happen in the industry rather than looking at a breadth of industries. Like, I mean, as Josh pointed out, like, you know, you could break open a Java book and see 8,000 patterns for how to do Java. And you like, and this is true of like every programming language that I'm aware of, right? You could look at Go and see a bunch of different patterns there. And we've talked about different patterns for just developing cloud native aware applications as well, right? I mean, like, there's so many options in software versus what we can do and what are available to us within networks. And so I think, yeah, I'm rambling a little bit, but yeah, I think that's the takeaway from this session, is that there's a lot of overlap and there's a lot of really great stuff out there. So this is Duffy. Thank you for tuning in, and I look forward to the next episode.
Yep, and I think we can all agree that Token Ring should have won.
Thank you, Josh, and thank you, Scott.
Thanks.
Thanks, guys. This was a blast.